funciona. Já colocou no YouTube, Eduardo? Tá. Então, boa tarde a todos. Vamos então dar início à sessão de hoje. Nós vamos ter inicialmente o professor Peter Diggle para dar um seminário para nós e na sequência teremos a Assembleia Geral da RBRAS. Então eu vou rapidamente só apresentar a RBRAS deixem-me só... desculpem, estava aqui a escutar em voz alta porque eu tinha o YouTube ligado, então estava a escutar a minha voz com um pouco de atraso. Então vou apresentar rapidamente a região brasileira da International Biometric Society. Então, a International Biometric Society, atualmente o presidente é o professor Gert Verbeek, da região belga, e o diretor executivo é o Peter, que está com base em Washington, que é também a base da IBS. A IBS ela tem aproximadamente 6 mil membros. Esse mapa com várias cores são os locais onde estão as regiões, então tem regiões em todos os continentes, então está bastante bem representado, e então tem um total de aproximadamente 6 mil membros. Os membros são mais ou menos organizados desta forma. Tem uma percentagem de 65% que são membros regulares, tem 13% de países em desenvolvimento, nos quais se inclui o Brasil, tem 2% aposentados e 20% são estudantes. Ao todo, a IBS tem 37 regiões, uma região usualmente está associada a um país, a RBRAS é uma delas, e tem 4 networks. Networks é como se fosse um conjunto de regiões que têm interesses, têm interesses similares e estão geograficamente próximos. Por exemplo, tem essas 4 que aparecem aí. A IBS tem um website novo que foi lançado há poucos meses, então o link aparece na tela. Será bom, pelo menos os associados, visitarem e verem como é que funciona, que existe uma área que todos podem acessar. E quem não é membro também pode acessar e ver se tem algo de interessante que possa contribuir para a sua profissão. A IBS ela tem várias publicações, ela publica o Biometrics e o Journal of Agricultural, Biological and Environmental Sciences, que são jornais de referência na área. Também tem o Biometric Bulletin, que ele é quinzenal, e também tem dois jornais que são associados a regiões. Tem o Biometrical Journal, que está associado à região alemã, e tem o Geostatistics e Epidemiology, que eu penso, não sei se é a região chinesa ou japonesa, é uma das duas. Então, existem vários benefícios dos associados da RBRAS. Eu listei aqui algumas delas, o site ficou um pouco cheio, mas acho que é importante falar um pouco sobre elas. Então, além do acesso grátis aos jornais, que normalmente as universidades também têm, também tem acesso ao Biometric Bulletin, que tem oportunidades de carreira, listas de congressos, notícias, etc. Também quem é associado à RBRAS também tem desconto em taxas de inscrições em congressos nacionais e internacionais, ou seja, tem a vantagem de ter descontos em congressos organizados por qualquer uma daquelas 67 regiões da IBS e também congressos nacionais como os congressos da ABE e da RBRAS. Também tem a oportunidade de conhecer e de interagir com os 6 mil membros da IBS. Os estudantes, eles têm também a oportunidade de participar em eventos da RBRAS e da IBS, e existem fundos de apoio para ajudar essa participação, então é uma vantagem importante. Nós criámos um fundo na RBRAS para estudantes, para apoiar a participação de estudantes. Naturalmente, nós exigimos que, eu penso, para estudantes de mestrado que sejam associados há pelo menos um ano, e de doutorado que sejam associados há pelo menos 2, que é o objetivo é manter os associados para não se associarem apenas para pedir o auxílio. Também existe um programa da IDS, que é o IDS Travel Award Program, que basicamente apoia principalmente participantes de países em desenvolvimento a participar em eventos da IDS e das suas regiões, então é algo bem interessante. Tem várias informações para membros no site da IDS, que apenas está disponível para associados. Na RBRAS, nós formalizámos a criação há um ano atrás, na Assembleia Geral, de um grupo de jovens pesquisadores, em que o objetivo é que esse grupo se organize e organize atividades mais interessantes para jovens dentro da RBRAS. E basicamente é isso. Eu acho que uma outra vantagem é fazer parte de uma associação que tem bastantes atividades. Nós tentamos ter bastantes atividades e, além disso, fazemos parte de uma família que é a IBS, que é uma líder reconhecidíssima a nível mundial. Quem se quiser associar à RBRAS pode visitar o nosso website www.rbras.org.br ou pode-me contactar a mim ou a Tassiana em qualquer momento para mais informação. Na sequência, eu vou passar a palavra ao professor Peter Diggle para fazer o seu seminário e depois vamos ter a Assembleia Geral, que vai começar às 15h15 em segunda convocatória e todos os associados estão convidados a participar, claro. E nós também convidamos os simpatizantes e que tenham algum interesse a assistir. Neste momento, só os associados estão no Google Meet, mas no final do seminário iremos partilhar esse link para o YouTube também, para quem esteja no YouTube e tenha interesse em participar, em saber um pouco mais da RBRAS, eventualmente se associar, poder também acompanhar. Naturalmente não terá direito à intervenção, mas poderá sempre assistir. Certo, eu vou parar aqui de partilhar a minha tela e vou apresentar o professor Peter Diggle. Agora vamos passar para inglês. Eu vou fazer a apresentação em inglês e depois o professor Peter Diggle irá continuar. So, Peter, I'm now going to introduce you, and then you can start your talk. Okay.
So do you make me presenter? Is that how it works? I don't usually use this system.
I think you can present. You can just go and present now. If you go down there, I think you have the option. So let me introduce Peter. It is really a great pleasure and honor for me to introduce Professor Peter Diggle, who is currently a distinguished professor at Lancaster University in the UK. Peter is one of the most well-known world statisticians. He was president of the Royal Statistical Society between 2014 and 2016. He holds currently appointments with the Faculty of Health and Medicine at Lancaster University and the Institute of Infection and Global Health at the University of Liverpool. In 1997, he was awarded with the Guy Medal in Silver by the Royal Statistical Society, which is a great honor. Between 2004 and 2008, he was also the EPSRC, which stands for Engineering and Physical Science Research Council. He was a senior researcher there. He's also one of the founding co-editors of the journal Biostatistics. Peter's main methodological research interests are in spatial statistics. He's going to talk a little bit about that today. Also longitudinal data analysis and environmental epidemiology. Most of his research is motivated by applications in biomedical, clinical, and health sciences. Peter has a particular interest in real-time health surveillance and in tropical disease epidemiology. During the time, Peter has countless scientific papers and contributions to the statistical development, and also a lifelong contribution to the field of statistics. I think most of you, every statistician, have at least read something that Peter wrote, or at least heard his name. I think I was when I was writing this introduction, I was thinking if I have ever met Peter in person. I think we haven't, but we almost did in 2016. I have to tell this. I was talking with Peter before a little bit before, and this is now is funny, but at the time was not so funny. So in 2016, I invite Peter to give a keynote talk at our annual conference at Arbras in Salvador. So long story short, Peter's flight was bought to El Salvador, the country, instead of Salvador, the city here in Brazil where I stand. So when arriving to El Salvador, he even tried to book a flight from there to here to Salvador. But from what I remember from our communication, it was expected to cost a few thousand euros. So he had to return to the UK. So that was really frustrating at the time. And well, now it is a bit funny, but at the time was really not. So today we don't have such a problems. We don't have wrong connections or missing connections. So I would like to thank again Peter for his availability to be with us today. And please, the floor is yours.
Thank you, Paolo. I'm just hoping I can now share my screen.
Yes.
Okay, and I should now fill that screen with my slides. Okay, is that okay?
We don't see that yet, I think.
That's a problem.
Did you go to present now? Did you select that?
I'm seeing. Okay, I'll try again. Present now. Present. Oh, present a window. Let's try that.
You can choose the PDF, maybe.
Yeah. Okay. Can you see that now?
Now it's coming. Yes.
Good.
Now, yes.
Good. Okay, I'm going to try and increase the size. Is that still good?
Yes. Now we can see it. Yes.
Okay. Well, thank you, Paolo, for that introduction, and I'm still very much hoping to come to the correct Salvador one day soon, and to renew my acquaintance with my many Brazilian friends, colleagues, and even relations, because my daughter-in-law is from the city of Salvador in Brazil, and we're hoping to visit her family there as soon as we are allowed to by our respective governments. So, talking today, if some of you got up very early in the morning, in the middle of the night, to hear me talk at the IBC in Seoul, Korea earlier this year, I'm afraid you're going to hear the same talk, apart from one or two very minor details. So I do apologize for that, but I hope for most of you who were not listening to me in the middle of the night when I was talking in Korea, some of this at least will be new to you. And I certainly would be very pleased to answer any questions. I think Paolo suggested that questions should go into the chat, and we'll take them at the end of the presentation. So without further ado, I will start by giving you a set of references to material that I'll refer to during the talk, but I want to say straight away that almost an identical set of slides is available on my website, so that if people do want to follow up the details after the talk, they should be able to do that by going to this site here. And I'm very happy for those slides to be shared. I left a copy with Paolo earlier today that he can pass on to anybody who's interested. I'm also not going to assume that you know anything at all about geostatistics. So I'm going to start with what I often use as a nice teaching example to show you the simplest kind of geostatistical problem. And a geostatistical problem in its simplest form consists of analyzing data which take the form of a set of measurements, each of which is located in a spatial region. In all of my applications, it's a geographical region, but the same methods can be used on microscopic regions, for example, looking at cellular structures under the microscope. And here we have a square about 7 meters by 7 meters. I think actually, sorry, 70 meters by 70 meters. The unit of distance is 10 meters, at which heights above sea level have been measured by a team of surveyors at various points in the region. And the objective is assumed to be to make your best guess, or to give it a grander name, your best prediction of the underlying spatially continuous surface of which these data are giving you some information. So we might assume that each y is a measurement on that spatial surface, like so, and the radius of the circle is an indication of its value. Or we might assume, and this is always the case in epidemiology, that the measurement is not exactly equal to the quantity you're trying to estimate, but it is related to it stochastically, and therefore it conveys information about it. And the canonical geostatistical problem is to answer the question, what can we say about the realization of S of X throughout A? So you can see qualitatively, without doing any analysis, that what we have here is a horseshoe-shaped ridge of relatively high elevations and a lower region in the north-central part of this small area. Schematically, we can think of a geostatistical model needing to accommodate the following ideas. Firstly, very often as we take data in a geographical region, the environment in which we're measuring those data changes, and sometimes it changes in ways which we can capture in covariate information. And so here we have a hypothetical environmental gradient running from west to east, along which we're occasionally taking measurements. And if we can assume that the only difference between the data represented by these circles and the underlying environmental gradient is pure random noise, then we can solve the problem of estimating the complete gradient using a regression model. What often happens in a geographical context is that when we can get an idea of the size of the sampling error or the measurement error of these individual data points, then stochastically speaking, they're too large to be dismissed as pure measurement error. There is also some spatial structure to them. So here I've, again, somewhat hypothetically in this case, I've posited an unobserved stochastic process, the realization of an unobserved stochastic process that captures the parts of the variation that we cannot fit by our smooth regression model, but it still leaves just the right amount in statistical terms of measurement error between the data points and the presumed underlying true surface, in this case, a transect running from west to east. So the idea in a slightly less simple geostatistical problem than the one I started with is how can you make the best use of both a regression model to take account of measured covariates and an underlying latent stochastic process to take account of spatial variation that is not captured by the covariates and the inherent imprecision of the measurements that you make to help you make inference about that underlying process. Geostatistical problems more generally fall into three categories, and this is not unique to geostatistics. It's true of many branches of statistics. There's the design problem, which in its simplest form asks the question, how should we choose the locations at which to collect measurements? If I can afford to take a given number of measurements, what's the best way to distribute them across the area of interest? Second kind of problem is estimation. And in particular, in geostatistics, the usual estimation problem that's of most interest is how to investigate relationships with covariates when measurements are spatially correlated. If they're spatially uncorrelated, regression modeling does that for us. If they're spatially correlated, we need that extra dimension of a latent spatially correlated stochastic process. And finally, prediction. And prediction in the areas in which I typically work is often the most important inferential question, often more important than estimation, and certainly much, much, much more important than testing hypotheses, which I haven't even bothered to put on the slide. prediction in its simplest form answers the canonical question of how would you map the outcome, or possibly its expected value, throughout the study region. I want to spend just a few slides on the history of geostatistics, and this first slide explains to some extent why it got its name, because geostatistics originally meant something far more specialized than spatial statistics. It was a specific reference to its origins in the mining industry in South Africa, and in particular, Professor Danny Krieger, who worked at the University of the Witwatersrand in South Africa. His name is immortalized in the word kriging, which is a well-used geostatistical technique. But the canonical problem in the setting of mining was that if this is basically an area of the Kimberley in South Africa, which it is, and if these parcels of land were sold to potential prospectors, what you would like to know before you commit to buying a parcel of land is what the likely grade of ore is that you can extract from that piece of land. And if before deciding what you were going to pay for that little square plot of land there, you had been allowed to take some exploratory measurements, not of the height above sea level, but of the grade of ore that you could extract from a core dug down at this point here, you would then have a very much better idea of how much value the square as a whole might yield if you were given the rights to exploit the mineral wealth lying under the ground. So a very practical problem led Krieger to promote the use of statistical methods in addressing these kind of questions. And as I said before, the geostatistical technique known as kriging is named in his honor. I think it's clear he didn't invent it. I think it was probably invented by Georges Matterhorn, who worked at the French School of Mines in Fontainebleau near Paris. And I didn't know this until quite recently, but he, being French, did his national service, and he chose to do it in the French Foreign Legion, and that placed him in Africa. And there he came across in his local library the early works of Danny Krieger, read about them, and his interest was obviously piqued because he very much developed la Geostatistics, as the French call it, as a self-contained body of methodology for prediction problems in the mining industry generally. And the French School of Mines is very, very closely associated with what I would now call classical geostatistics. The important thing to note there from the point of view of the history is that this was all done without any reference to the mainstream statistical literature. And Matterhorn developed his own terminology and notation and inferential methods without any real interconnection with classical statistical methods. Not only that, but in Europe at about the same time, now in Sweden, Bertil Matern, the late Bertil Matern, was a senior statistician in the Swedish Royal College of Forestry in Stockholm. And he promoted the use of spatial statistical methods for sampling forestry data, and in particular for estimating the yield of a forest by analogy with the original problem in South Africa of estimating the yield of a mineral mine. And again, Bertil worked, to the best of my knowledge, he never met Matterhorn. Also, for most of his career, he didn't, again, interact with mainstream statistical methodology very closely. But he did have a number of friends who we would recognize as mainstream names in statistics, including Professor Peter Whittle at Cambridge, who spent a sabbatical year in Sweden. And he was invited to give some lectures at Imperial College towards the end of the 1960s. And they were a great success. And the audience said, where can we read about this work? And it was not published in conventional journals. It was essentially all published in his PhD thesis. And so what then happened was that Bertil Matern agreed that people could simply photocopy his thesis and distribute it. So in fact, it was slightly more organized than that. And when I started my life as a research student in 1972, the first thing that I was asked to read was Bertil Matern's thesis, which now came in a slightly amateurish binding, but basically photographed from the original thesis. And every student of the then emerging discipline of spatial statistics would read Bertil-Matern's thesis. It's full of ideas, not restricted to geostatistics, but including many of the ideas that Matterhorn developed independently in France. Now, the other way in which geostatistics got into the statistical mainstream was through the efforts of these three statisticians here. Jeff Watson at Princeton spent a lot of his work not doing geostatistics as we now understand it, but certainly working with geological scientists. And he wrote several papers in the 1970s explaining stochastic process prediction to geological scientists. And that is the mainstream statistical connection, because those of you who know your history will be aware that stochastic process prediction can be traced right back to Kolmogorov's work in the 1930s. And so this is a very good example of the old phrase that there is nothing new under the sun. Now, Brian Ripley, to my knowledge, was the first person to write a book aimed at statisticians, which included a chapter, a rather concise chapter, re-expressing conventional geostatistical methods like kriging as applications of stochastic process prediction a la Kolmogorov back in the 1930s. 10 years later, Noel Cressy wrote a much bigger book on spatial statistics, which is still a standard reference work, and he classified spatial statistics under three broad headings: lattice data, point process data, and geostatistics. So Cressy wrote essentially a book within a book, because the whole book has about 1,000 pages, and several hundred of those pages were devoted to a systematic account of geostatistics, but in language that was familiar to statisticians. And very quickly after that, geostatistical methods started popping up in all sorts of areas of applied statistics. So that's geostatistics into the statistical mainstream. Now, myself and two colleagues, Rana Moeed and Jonathan Torn, wrote a paper in 1998, which we called model-based geostatistics. And at the time, one or two people couldn't understand the title because they said all geostatistics is model-based. And perhaps they had a point. But the reason for us writing that paper was that, having basically discovered all of the geostatistical methods that were expressed in their own language, their own terminology, as I said earlier, without reference to the mainstream statistical literature, what myself and my two colleagues tried to do in 1998 was to embed geostatistical principles of statistical modeling and inference to the solution of geostatistical problems. So, to summarize, really, I would argue there's no such thing as geostatistical methodology. There is just statistical methodology. But a geostatistical problem is a classification of a set of scientific problems for which general statistical principles can be applied, and some of those would duplicate what most people regard as classical geostatistics. Others do not duplicate them, but are genuinely new methods. But the aim was to try to shift the emphasis away from a particular set of methods to a particular set of problems which could be addressed by standard statistical methods. And so this slide tries to summarize my general approach to this and other statistical problems, which is that statistics ultimately has a role to help scientists understand nature. I include in the phrase scientists, social scientists, natural scientists, medical scientists, and I could, if pressed, stretch to economists and people working in commerce in other sorts of ways. But fundamentally, what scientists want to do is understand nature. And the way they gain an understanding of nature is in two very different ways. Scientists develop an understanding of nature by theorizing about it. And when they theorize, they build models. And I'm calling those process models. They are models of a natural process. Because scientists also build their understanding of science by conducting experiments or observational studies. And those studies generate models, but these are different models. These are models for the data that the scientists have collected. So now we have a goal, but we have two different ways of advancing that goal, and it leads us to two different kinds of model. And the role of statistical inference, it seems to me, is to be the bridge between those two approaches to science. The empirical approach that gives you models for data, the theoretical approach gives you models for processes, and statistical inference is the bridge that brings those two things together. Expressed algebraically, we have an unobserved process S. S I use because I think of this as a signal, and also, of course, I'm dealing with spatial processes. Y is a set of data that's relevant to understanding S, to understanding the underlying signal. If you want to proceed taking advantage of both your scientific knowledge and from your theory and your empirical evidence from your experiment, you need to set up a hierarchical model, because the model for the unobserved process exists independently of the data, and any model for the data must be conditional on the state of nature. And so the classic way to formulate a model for scientific problems as I envisage them in this triangular representation is through this hierarchical representation, which implies a distribution for any property of S that you're interested in. So T here, T for target for prediction, is any property of S in which you have an interest as a scientist. And using Bayes' theorem, you can convert your hierarchical model to a conditional distribution for the signal S given the data Y, and a fortiori for the any property T of the signal S given the data. And so that's why prediction is right at the heart of geostatistical problem solving. But I've suppressed in this equation any mention of parameters. So we also need to solve estimation problems. My preferred method for doing that is through Monte Carlo maximum likelihood. Well, sorry, I should say my preferred method for doing that is maximum likelihood. And in the problems that I'm going to be dealing with in the rest of the talk, the only way I can implement that is through a Monte Carlo method. If people would rather use Bayesian methods for their parameter estimation, that's fine, that's their choice. And I don't think the distinction between the two is often terribly important. Whereas the focus on prediction problems rather than estimation problems is important and is central to the kind of solutions that geostatistical models can provide, as I hope now to convince you. So first, continuing this emphasis on prediction and building my slide on a very wise saying by Peter McCulloch, the professor of statistics at Chicago, the answer to any prediction problem is a probability distribution. What Peter should have said, of course, is that the honest answer to any prediction problem is a probability distribution. So to some extent repeating the previous slide, but making the role of my target for prediction explicit, S represents the state of nature, Y represents all data relevant to understanding the state of nature, T, which is some functional of S, is the target we're trying to predict, and our model is specified hierarchically as a marginal for the state of nature times a conditional for data given the state of nature, and prediction involves in inverting the conditioning so that we end up with a target for prediction T given the state of nature. Now, when we're making predictions, we have to recognize that we will have parameters and we probably don't know the values of those parameters. We could be optimistic and simply plug in a point estimate of our unknown parameters. We could be more cautious and arguably more honest by weighting our predictions according to our uncertainty about those parameters as expressed by a sampling distribution. Or, if we prefer, we could be Bayesian and replace the theta hat by an unknown random variable theta, and then theta conditional on y is the Bayesian posterior, and for the predictive distribution we're marginalizing with respect to the posterior. And it's the fact that this looks very like a Bayesian inference that leads me to have said a couple of minutes ago that in the context of geostatistical prediction, whether you prefer to use maximum likelihood or Bayes for your parameter estimation is usually not very important. Now, the rest of the talk is based on two case studies which illustrate different kinds of modeling and inferential challenge. The first one is an environmental monitoring problem coming from a pollution study in the northern part of Spain. And what we have here is a map with two sets of locations marked. The 1997 sample in blue, you can see, is rather irregular and predominantly in the northern part of this region. The 2000 sample, 3 years later, in red, you can see is much more like a regular grid, although there are some deviations from that regular grid, for reasons I suspect to do with practicality of not being able to sample in built-up areas, because what's being sampled here are lichens growing on trees, which are then assayed for their lead concentrations. So the problem here is to use lichen as a measuring instrument for the degree of lead pollution in the atmosphere throughout the province of Galicia, and to draw a pollution map and to make inferences about the state of pollution across the province of Galicia, and in particular to compare the 1997 and the 2000 maps. Now, the methodological problem that this arises is, if I'd only shown you the red points, you'd have thought, well, that's very clearly a systematic coverage of the region. When you see the blue points, you have to ask the question, why is there this predominance of points in the northern half of the region? And there's a potential here for a form of selection bias, because if the concentration of blue points was based on a suspicion that that's where the pollution was worse, then there's an obvious potential for bias if you try to use these data to estimate pollution across the whole of the province. If it was for other reasons, all may be well. There's certainly no theoretical requirement for data to be sampled in a regular grid in order to use geostatistical methods, but there is a requirement, if standard geostatistical methods are to be used, that the sampling is unbiased in the sense that it is not being informed by the values that you're trying to measure. Now, that problem is what I called in a later paper with two collaborators, one of the references I gave you earlier, preferential sampling. And preferential sampling refers to a stochastic relationship, and I emphasize stochastic, between the signal, this underlying state of nature about which you're trying to make inferences, right? And another stochastic process, which is where you take the measurements. So in other words, if your design for the study, choosing your locations, is stochastic, then there's an implicit assumption in classical geostatistics that that process is independent stochastically of the signal process. Now, what's happening in terms of joint distributions is that the conventional geostatistical model says that if I have a stochastic sampling rule, which of course I should have, because sampling should be probabilistically based if it's going to be unbiased, and I have a stochastic state of nature, and I have stochastic data Y, then the factorization that's implicitly being invoked with standard geostatistical methods is a marginal distribution for S, another marginal distribution for X because it's independent of S, and a distribution for the data that's only dependent on the underlying state of nature S at the points where you measure the data. The preferential sampling model that myself and Tingley Sue and Raquel Meneses introduced a few years ago now says that for those same three stochastic objects, nature determines S. We then determine X conditional on S when we take our measurements, and we may have a stochastic dependence there, or we may not. We allow the possibility. And then the data are a fortiori conditioned on both S and X. And the key point for inference is that algebraically, this distribution here may well look as if it's just Y given S. But what it actually is Y at location Xi depends on S at location Xi. And if Xi is stochastic and dependent on S, then you need to condition on them both in order to get a valid inference. So, not because I think it's a flexible enough model to use for all applications, but because at the time it was a topic that hadn't really been discussed, the three of us put forward a rather optimistically simple model for preferential sampling of environmental pollution data, namely that conditional on the underlying state of nature, the points at which the measurements are made are an inhomogeneous Poisson process with an intensity that's log linearly dependent on that underlying process. So I emphasize this is a qualitatively sensible model in the sense that a positive beta means you're oversampling where the S of X is high, a negative beta means you're oversampling where it's low, and a zero beta means it's independent and you can use standard inferential methods. But it certainly is a long way away from a sufficiently flexible model for all applications. We presume, as most geostatisticians do, that conditional on the signal, and in this case, the locations as well, because they're stochastic, the measurements are independent. And in this case, because it's a continuous measurement, I'm assuming it's Gaussian. Actually, I'm assuming that it's log Gaussian, so I've log transformed it for the Gaussian assumption. There's an overall mean, which varies according to the local value of the stochastic process, and there's a measurement error variance tau squared. And this is where we developed an important sampler for Monte Carlo evaluation of the likelihood, and therefore we're able to construct Monte Carlo maximum likelihood estimates. And we were able to apply these methods to the environmental monitoring data. The strategy we adopted was firstly that we assume the grid sample is non-preferential. It's hard to imagine how it could be, but at least to a great extent. If the sampling is as regular as this, it doesn't look as though there's any bias. The 1997 sampling, however, we accept may be preferential, but after some exploratory analysis, we made the problem more identifiable, essentially, better posed, by postulating that some parameters might be held in common between the two years. And we checked that by some inferences. Because we're working within a likelihood framework, we can look at likelihood ratios as a way of model comparison. So if we do a simple analysis, ignoring any considerations about preferential sampling, we can either fit the model with free parameters to both sets of data, the red and the blue, or we can impose a common covariance structure, and you can see that the log likelihood ratio is really just about acceptable. In fact, in conventional significance terms, it's highly acceptable because the covariance structure involves at least two parameters. Depends exactly on how you parameterize it, but it's at least two parameters and more likely three, because we've got a variance, a correlation, and a measurement error variance. And so that difference in the log likelihood is pretty much acceptable. However, if we allow the 1997 sampling to be preferential, we still find that it makes little difference in likelihood terms whether you impose a common covariance structure or not, but you can see that the change from the non-preferential assumption is very substantial. And by any measure, which is simply only estimate, since it's only introducing an extra parameter, a single extra parameter is clearly highly significant. So there is evidence there for preferentiality in the 1997 sampling. Does it make a material difference to the predictions you make? I would argue yes. Remember that we modeled these data on the log scale, but what I've done here is I've put them back to the pollution scale. And the reason we have a scale running from the negative to the positive is because one of these maps is the difference between the two sets of predictions, and I wanted to use a common scale. So you can see that for the simple analysis, we have these patches of high pollution, the yellow patches there. And for allowing for the preferentiality, we actually have more pollution overall and a much, much broader encompassing of that those highly polluted areas through the central belt and to the northwest. And the difference on the same scale is not trivial. Now, in fact, the preferential sampling here turned out to be preferential in the favor of small values of pollution. So in fact, the more highly polluted areas were undersampled. So I hope you agree that example shows that sometimes if you question the standard assumptions of a geostatistical analysis, you find interesting things that really need to be taken into account. But certainly, in order to do that, it was important to have two sets of data separated in time and to be able to make some simplifying assumptions about one of them, namely the 2000 data set, in order to make my parameters well identifiable. Okay, so now I want to get on to the last part of my title, which is how does this help us achieve better global health? And I like introducing this segment of the talk with this photograph because it illustrates fundamentally that we're dealing here with problems that affect communities, and they affect communities living in difficult situations. And the people who are trying to help them, who include this man on a motorbike who is an epidemiologist on a field trip, they are very resource limited in ways that would not apply to the same extent in Brazil or the UK. And therefore, in order to understand, in this case, variations in health outcomes across the geography of regions which are populated like this, you very often have to deal with sparse data. And in particular, this person is trying to establish the geographical variation in prevalence of a very serious public health problem in sub-Saharan Africa, namely onchocerciasis or river blindness. Now, if river blindness was a problem in the UK, we would have a national registry of diagnosed cases of river blindness, and we will be able to look directly in that national registry and get precise estimates of the geographical variation in incidence. In environments like this, no such registries exist. So I won't take you right back through the slides, but remembering again my very opening simple slide, if you now think of the circles on my original data set as not being heights above sea level, but being estimates of prevalence at village locations in Burkina Faso, then you can imagine that to collect data of that kind is a very, very major effort. And so one has to do the best job one can of mapping the prevalence of the disease using less than ideal study designs and less than ideal sample sizes. This epidemiologist is on a 4-week field trip, and he left the capital of Burkina Faso driving a Land Rover. And when the roads gave out, he unhooked the motorbike from the back of the Land Rover and carried on as he penetrated deep into the rural heart of Burkina Faso. This is not Burkina Faso, this is Liberia, but the program that gentleman was working on is actually an Africa-wide program spanning more than 20 African countries, all of which are particularly badly affected with onchocerciasis. And in each country, the aim of collecting the data was to be able to map variation in prevalence throughout the designated region in order to inform the treatment strategy. Because there is an effective way to protect people against river blindness by taking prophylactic medication annually or at most 6 monthly, but supplies of that medication are limited. And in particular, the distribution of that mechanism is a major logistic problem. And therefore, it's important to prioritize high prevalence areas for treatment. So, how many samples do we need to take? Where should we take them? And how should we analyze the data when we've got them? And those are the 3 questions that I mentioned earlier, namely design, analysis, and prediction. Now we're dealing with prevalence data, and prevalence data mean binomial sampling, because at each village location you take 50 to 100 people and you test each of them for the presence of river blindness parasites in their blood. And that would generate binomial data, and therefore if you're trying to understand the variation in that binomial outcome, you would naturally think not of a linear model, as I did for the pollution data, but of a generalized linear model, and in particular, a logistic regression model. But just as in the earlier example and in my original schematic, we can't rely on a classical generalized linear model because we may not be able to account for all of the spatial variation through measured covariates. So we have the same general idea that we have a latent, spatially correlated process S of X, which is at least partially driving the variation in prevalence, and we would rather like to predict what that process is doing in each of the African countries of interest. Also, whenever you collect prevalence data on people, you will be aware that their risk of acquiring disease is not merely a function of place. It's also a function of other attributes which they possess. They may be genetic, they may be behavioral, and also, although you can associate them with the place where those people live, there's no reason to give them a spatial structure. And so we also allow another latent process, which is in fact a set of IID normal random effects. So basically extra binomial variation. We then invoke a familiar generalized linear model, namely the logistic regression model, but with the addition of these two random effects, the spatially correlated one and the spatially uncorrelated one, into the linear predictor. Other than that, it's just a logistic regression model. If we apply that model to our Liberia river blindness data, you can see that the map has a very strong face validity, in the sense that where the data indicated high prevalence, we're typically predicting prevalences up as high as 30%, and where the data indicated low prevalence, we're more likely to predict prevalences around about 10%. You can also see a general trend moving northeast, and that's because we put distance from the coast in as a covariate based on local information that the vector that spreads this disease does not thrive in coastal areas. What it likes is hot, wet areas that are typically found inland, away from the relatively dry and relatively cool coastal strip. So there we have our best single guess at the variation in prevalence of river blindness in Liberia. But it's only a guess, and we'd really like to go a bit further than a guess. So how do we indicate the precision or the trustworthiness of our guess? What we like to do in the group that I work with in Lancaster is use exceedance probabilities. So on the left, instead of mapping our best guess at prevalence, we're mapping the predictive probability that prevalence is greater than 10%. And what this is saying is that we are almost certain that most of the country has prevalence greater than 10%, the only exceptions being this coastal strip. And there's this small, if you like, intermediate zone where the call is around about 50-50. Yellow, pure yellow is 50-50. But certainly all of these inland regions, they are highly likely to have prevalence greater than 10%. Now, if instead of working with the prevalence of 10%, you work with a higher prevalence, clearly you will be less certain. And that's what this map shows. That now there's a much smaller set of areas where we're nearly certain that prevalence exceeds 20%, much bigger zone of uncertainty, and a much bigger area where we're confident, we're pretty certain it's less than 20%. Now, this is an important number because it wasn't my number. The WHO guidelines for prioritization of the distribution of prophylactic treatment for river blindness are that areas should be prioritized if their prevalence is greater than 20%. So I would argue that apart from conveying to a statistician the level of uncertainty about your predictions, because as a statistician, we could clearly use any number here and we could actually tap through a range of prevalences from 0 to 100% and see the map changing. More importantly, this answers a policy relevant question, because the WHO would do exactly the same in an area that has prevalence 20% as in an area that has 30% or 40% or 50% or 60%. So establishing where we are certain that we do exceed 20%, certain that we do not exceed 20%, or honestly uncertain, is actually answering the policymaker's question. So I like these exceedance probability maps both because they convey statistical imprecision in a way that I find intuitively natural, but also because they focus attention on the policy relevant question rather than arguably the much less relevant question of what's your best guess at what the prevalence actually is. Now, I want to show this example because the way decisions like this are currently made in most tropical disease epidemiology is by using classical binomial sampling theory. So we imagine that we've got a set of independent binomials and we take as our inference a confidence interval for the true prevalence. Now, it may be on a whole country level, or it may be, and more often is, on a level of districts within a country. But typically, not universally, I have to say, but typically, the inference is simply based on a confidence interval for the prevalence and how, does that confidence interval exclude or include 20%? If it includes 20%, you're uncertain. If it excludes 20%, you're reasonably certain one way or the other. So I want to show how that works in a simple simulated example. So this is a hypothetical prevalence surface for which we actually know what the truth is because it's a simulation. And the area-wide prevalence in this region is 41.7%. We measure the prevalence at the sample locations. It will not have escaped some of your attentions that I'm using my initial teaching example as the basis for the simulation, but I'm simulating a prevalence surface. And if I apply classical survey sampling statistics to these data, treating them as an independent random sample, I get an estimate which is very close to the truth, which I should because it's unbiased, with an estimate of uncertainty based on a confidence interval, which is plus or minus 8.6. If I do a geostatistical analysis, I get almost the same point estimate, which is typical for the area-wide average, but an order of magnitude smaller error. And the question is, why do I get that dramatic improvement? And it comes from two different sources. The first source it comes from is that the geostatistical approach is able to exploit spatial correlation, because spatial correlation means that if I have a datum at a particular location X, that datum is informative of prevalence not just at X, but at neighboring locations. And what do I mean by neighboring? Well, that depends again on the data, because by fitting a model to the data, what I'm doing is I'm choosing the optimal definition of neighboring by estimating the scale of spatial correlation. And so there's an inherent advantage to having spatial correlation when you're trying to predict an area-wide average. The second and often bigger gains come from asking the right question, because implicitly what that classical approach was doing based on survey sampling was asking how precisely you can estimate prevalence under repeated realizations. Whereas what we want to do is to predict prevalence based conditioning on this particular realization. And that turns out to have a big dividend. Now, what we're working on mainly at Lancaster these days is neglected tropical disease programs in various parts of the world for various diseases, but they all come under this banner of neglected tropical diseases, which is in fact a formal list maintained by the WHO, and you can find out more about it if you wish by going to the WHO's website. But the striking quote about neglected tropical diseases is that despite their being neglected, actually 1/6 of the world's population are infected with one or more of these neglected tropical diseases. Now, a map doesn't tell the whole story, and of course the whole of Brazil is not as badly affected with neglected tropical diseases as is the majority of South Africa. There are a lot of neglected tropical diseases somewhere in Brazil, but as I'm sure you all know, they're rather focused in the poorer and more remote regions of Brazil, whereas in Africa there is an enormous problem, and certainly a very clear majority of all these people are people who live in Africa. So we have some sustainable development goals which we're all supposed to be working to. And these include goals specifically to do with public health. And the most ambitious of them involve eradication of a disease, which means permanent reduction of its incidence to zero. The only disease I'm aware that we've eradicated so far in modern times is smallpox. Elimination in tropical disease development goals means reduction of local incidence to zero. So we can declare particular areas free of a disease. And even less ambitiously, but still ambitiously, really very ambitiously, these are all very ambitious goals, but this is the least ambitious of three all ambitious goals, if you see what I mean, is to eliminate the disease as a public health problem. And that means reducing the incidence locally to an agreed level. And so policies for the control of neglected tropical diseases are based around threshold prevalences that experts in the disease in question have agreed would be low enough that it's a copable problem as an endemic problem. In other words, and you'll begin to see that there are echoes of our current situation worldwide here. We may not be able to get rid of these diseases, but if we can reduce their incidence to a manageable level, we can keep them under control and life can go on. So my last case study involves lymphatic filariasis in Ghana. Lymphatic filariasis, like most of the NTDs, is not a lethal condition, except in rare cases, but it's a very seriously debilitating condition which affects the quality of life of a very large number of people. So, in order to demonstrate, we hope, the advantage of adopting geostatistical methods for mapping prevalence of neglected tropical diseases and therefore judging the extent to which these development goals are being achieved, we were able to access some data from Ghana on the prevalence of lymphatic filariasis before there had been any interventions designed to reduce its, what you might call its natural distribution. And so we were then able to fit a model to those data, and using that model, we were able to forward project what the geographical distribution of lymphatic filariasis would look like if interventions had reduced the prevalence to the agreed elimination status level, which for this particular disease represented a prevalence of 2%. We then were able, using our simulated geographical distribution of lymphatic filariasis as elimination status, to compare two design strategies. One is the current WHO guidelines, which are of the kind I've already described. In fact, as I may have time to tell you, they're actually even cruder than that. And the other is model-based geostatistics. The investigation was led by my colleague Claudio Frontera and is now published. So the WHO guidelines are as follows. You consider each district as an evaluation unit. An African country typically has something of the order of magnitude, depending on its size, of 20 or 50 or 100 districts. And within each district, you use tables that WHO provides. And so the district health authorities are told how many villages to sample, how many children to test per village. They then simply count up the total number of positive test results without any reference to where they came from. And if that number exceeds a number in a table, they declare elimination not indicated. And if it is smaller than the number in that table, they declare elimination as indicated. So there's no inference other than a simple yes-no binary classification according to one count of the total number of cases. Now, the way we approach this as a geostatistical problem is that what we're really trying to get at, our predictive target, is the population weighted prevalence of disease. So if the risk of disease or the probability of catching this disease at a point X is P of X, then if nobody lives there, we don't much worry about that. So we have a weighted average of the prevalence across a large but fundamentally discrete set of rural communities in Ghana. And the WHO tells us that elimination is deemed to have been achieved if and only if that population-weighted prevalence is less than 2%, 0.02. So what we do is we fit our model, which again is a geostatistical version of a logistic regression model because we're dealing with prevalence data. We draw samples from the predictive distribution of T. We choose a probability threshold Q, because remember Peter McCulloch said that the honest answer to a prediction problem is a probability distribution. And our rule would say we will have elimination indicated if the probability that the WHO threshold is achieved, conditional on the data, is greater than Q. And if you set Q to be 100%, of course, you will never indicate elimination. So it seems to me it's better to acknowledge that you can never be certain than to pretend you can, which is what the current method does, and actually agree on some value of Q close to 1, which indicates your appetite for risk in terms of whether you will or will not declare the disease to have been eliminated. And remember, elimination does not mean eradication. It still holds open the possibility, and one hopes the actuality, of monitoring the disease for future recrudescence. But it does mean that scarce resources can be diverted to other parts of the country where elimination has not yet been achieved. So the data set is really quite rich. You can see we had data from 403 locations covering a very wide range of empirical prevalences from close to 0 right through to greater than 50, and with some obvious spatial structure with these hot areas in the north and south and cooler areas in the rest of the country. We analysed those baseline data for spatial correlation. If you haven't seen a variogram before, here is one now. And the way to think of the variogram, if you look at its definition, because it's a variance of a difference, the variance of a difference when a distance is small is likely to be small, because if these two random variables are highly correlated, the variance of the difference will be small. But as the locations become more separated, one might expect the spatial correlation to weaken and therefore the variance to increase, until ultimately, if these are independent random variables with the same variance, then what you will be measuring here is the variance of S of X. So you have this textbook picture of a variogram as a function that increases from something close to, but not necessarily equal to 0, because our data will have measurement error in them, or in this case, binomial sampling error. But the indication is that the correlation decays, and the blue envelope is saying, what do we think statistically that variogram should look like if the data were completely uncorrelated? So we have an indication that the correlation is extending over something of order of magnitude 100 kilometers or so. But more importantly, we have an idea that it's a nice monotonic function that we could reasonably model parametrically, which we did with an exponential. We can therefore draw prevalence maps either as continuous maps, which we've done on the left here, or as a choropleth map based on the Ghanaian districts, which is more relevant because the districts are going to be the areas that we're going to advise are or are not successful in eliminating the disease. And notice that we still model on a continuous scale, and we then integrate the predictions. What we do not do is aggregate the data. Our model projects forward in a way that simply shifts the log odds so that the countrywide average prevalence is 2%, because that's the elimination target. And we would only be conducting tests of elimination when the country has anecdotal evidence that it's about at the level that it thinks it can essentially applies for certification of having succeeded in eliminating the disease. And again, those maps can be drawn as spatially continuous maps, or more usefully as choropleth maps at the district level, okay? And so at baseline, you can see that the very large numbers of districts for which the probability that they were less than 2% at baseline is essentially 0. To simulate progress towards elimination, we shift the log odds. think I mentioned that a bit earlier on the last slide. So we fit our model to the baseline, and then we shift the log odds so that the population weighted average of P0 of X is 0.02. And now our prevalence maps look completely different. We can see that on the left, they're now almost entirely blue. And when we aggregate them up to districts, there's only a couple of districts in the northwest that are not blue. There are quite a few that are light blue, though, and light blue means that there's certainly some indication there that we're above threshold, even though we're not very far above threshold. And again, to relate that to the policy, it's much better to actually map the probability that our districts are projected to have achieved elimination status. And you can see now here a more nuanced picture, because we now have quite a few districts still where the probability that we've achieved elimination is pretty close to zero, but rather more districts than before where we're pretty sure that they have eliminated the disease as a public health problem. Well, how do we decide whether this methodology is any good? Well, this is a simulation, but we have followed it up with a number of case studies, which I would be happy to talk about on another occasion. And so what we do is we simulate test results over the region of interest, and we apply both the current WHO guidelines and our model-based predictions to the simulated data. And we then compare the actual and the indicated elimination status. Because we're simulating, we do know what the true status is of each district with respect to that 2% prevalence threshold. And we can indicate whether or not we think it's eliminated it based on either of these two methods. And for our method, of course, that means we're sort of free to choose the probability threshold at which we declare we're pretty certain that prevalence is less than 2%. Then we construct tables of true and false, positive and negative indications across all the districts of Ghana, and we calculate their positive and negative predictive values and display them on an ROC curve. So focus now, please, just on the top left. This is where we use exactly the number of sampling locations indicated by the WHO guidelines. And if we apply the WHO rule, which if you remember was a deterministic rule, then there is no ROC curve. The positive and negative predictive values are simply numbers, because there's no flexibility in the methodology. And you can see that the WHO guidelines here are putting quite a high premium on getting a high positive predictive value, 95%-ish, but they're not great on their negative prediction value. Okay, this is 1 minus the negative predictive value, so the predictive value is about 70%, right? Now, these curves here, they're almost identical. They're based on two different sampling designs using the same number of data points as the WHO guidelines, but analyzing the data geostatistically and varying the probability, the predictive probability at which you would declare elimination. And you can see necessarily that because of that flexibility, you can either put a very high premium on positive predictive value or on negative predictive value. But what's clearly the case is that you can do better than the WHO guideline on both measures by quite a substantial amount. Now, what's more impressive is that we can also apply our geospatial method with sampling 1/5 the number of locations. And here we still do slightly better than the WHO. The WHO cross here hasn't moved. It's still using the full set of locations. We're using 1/5 of them. And so the cost saving implications of that, if you have to run an elimination survey, are really very substantial indeed. If we push our luck a bit further and go down to 1/10 the number of locations sampled, then we don't do so well. The second row is a little bit more speculative, but if we make an additional operational assumption that the cost of running an elimination survey is primarily driven by the number of locations and not by the number of people you test, what we've done in the bottom row is we've started in the same place, but as we reduce the number of sampled locations, we increase the number of people sampled. And basically, we just about preserve our full predictive power with a smaller number of locations, because the binomial sampling variation we've tamped down to something much smaller. And because the spatial correlation in this case was very strong, extending over something of the order of 100 kilometers, we really don't need to take very many locations in each district in order to get accurate predictions. So the WHO guidelines said 30 locations per district. 5-fold reduction takes it to 6, and 10-fold reduction takes it to 3. So I did say earlier that these methods are really particularly well suited to tropical disease applications where you don't have accurate disease registries. And of course, in our complacency in the UK, we were singularly ill prepared to deal with the COVID-19 epidemic when it arrived. And so we are now within the UK conducting sampling for prevalence of COVID-19. And these maps were produced fairly early in the epidemic, back in about April, when it was really a very, just about at its height. And you can see that across the UK, about a month into the epidemic, the percentage of users reporting current positive symptoms could be as high as 7 or 8% in some parts of the country, but as low as 1.5% in other parts of the country. And in particular, those of you who know your British geography will spot that on this map, which is where I've shown the probabilities for each locality of exceeding the national average, those high probabilities are in big conurbations. We've got the Scottish cities of Glasgow and Edinburgh, biggest Scottish cities. And then in England, we've got Newcastle upon Tyne, Liverpool, Manchester, Birmingham, London, Cardiff. And for some reason that nobody really understands, Bristol in the southwest has done pretty well throughout this epidemic and has had much lower prevalence. And you can, again, because we're sampling from predictive distribution, we can gauge the precision of those predictions by looking at quantiles of the distribution if we wish. And frankly, these estimates are pretty imprecise, but it's good to know that if you're trying to make policy decisions based on them. There are now bigger randomized sampling surveys being conducted in the UK, and there are maps available now which are operating to much greater precision than this. But again, we're a long way off having comprehensive diagnosis of COVID-19, and so geospatial methods of the kind I've discussed in Africa are just as relevant in the UK. So just to conclude, the methodology that I've been describing here is really not very new, except in detail. It's been developed over about 20 years now, and there are a growing number of case studies to show, I believe, convincing evidence of its usefulness in tropical disease epidemiology in particular, but in a range of environmental and public health problems more generally. But the sort of methodological extensions that the practical problems we work on have thrown up include really quite a long list. And one of the perhaps less obvious ones is multiple diagnostics. It's again particularly the case when resources are limited that you might not always be able to use the best diagnostic tool, but you can clearly get information from a poor diagnostic if it's at least correlated with a better diagnostic on which you also have information. And so that could also add to precision. Equally, we can sit in our comfortable offices and advise randomized sampling, but inevitably in low resource setting, you are invited to analyze convenience survey data. And provided you can anchor those convenience survey data in a small randomized sample, you can, with a precision that needs to be quantified, adjust for the bias in the convenience data. Thinking about my friend on the motorbike doing his 4-week field trip, it would be much more efficient use of his time if he could jointly sample for more than one neglected tropical disease at a time. And until recently, the neglected tropical disease world suffered from a silo operation in which different teams were working on each separate disease. And there's beginning to be a move towards joining those teams up so that you can jointly sample for several diseases. And again, if the prevalence surfaces are correlated with each other, then you can borrow strength across those dimensions and get better information. Adaptive design is fairly self-explanatory. Rather than having to say, take the following locations and then you're done, if you can do a pilot sample, analyze the pilot sample and go back and refine your knowledge where it's uncertain, there can be considerable gains in efficiency. If you remember quite a long time ago now, my map of Liberia, where I described the exceedance probability map as defining an area where we were sure that disease was greater than 20%, an area where we were sure it was less than 20%, and a zone of uncertainty, if I could afford to take more samples, I would focus them on that zone of uncertainty. Spatial temporal models have an obvious relevance in general. The diseases that I'm currently working on are generally endemic, and purely spatial models are okay. But certainly the work on COVID at the moment very definitely needs spatial temporal models because the epidemic is still evolving in most countries of which I am aware, certainly including the UK. I think the UK, the USA and Brazil have all got serious problems with COVID, which may or may not be a reflection on their respective governments. I suspect it is, frankly. And of course, the methodology doesn't know about why you're trying to estimate prevalence. It could be any georeferenced numerator denominator data that is relevant to the area of science you're working within. All of the software we use is in an R package, which is continuing to have its functionality increased. And the thing that we're currently really quite excited about is the prospects of developing a more interactive user interface that people in low and middle income countries can use with minimal external interference, because the more that people in country have ownership of their data and their analysis, the more they will be able to use it in a timely and efficient manner to help solve their country's health problems. Thank you very much for your attention. I hope I haven't talked for too long. I can see that I have. I can only apologize for that. And I'm now going to stop presenting.
Thanks, Peter. Nothing to apologize. I think it was a pleasure for all of us to listen to you. So now we can open the discussion. We can have like 3 or 4 minutes for discussion. If anyone in Google Meet has a question, you can unmute your microphone and ask directly. If you are in YouTube, please write it down. You can write it down either in Portuguese or in English, and I can translate it.
Oh, can I make a question then?
Yes, of course.
Peter, there is now an explosion of new spatial data. First, thanks for the talk. It was a great talk, a great overview. I love the historical slides that you show in the beginning. I never saw a picture of Krieg and Matern. Was nice to have now a face connected to the methodology. But the question is, there is now this explosion of new spatial data collections, such as ways, trajectories, allocation of tasks to agents like Uber or food delivery apps, or cellular phone movement to verify the degree of social isolation in terms of the COVID. For one side, there is much statistical regularity in this data collection. The data is huge, so statistical regularity appears. But for the other side, they need very quick decisions in face of unexpected emerging patterns. So how do you think our statistical methods should approach these new data collections that require this type of decision making?
Well, I think the thing that always concerns me is that a lot of the biggest data collections are collected in a way where you can't be sure they're free of bias. And bias really kills you after a while, because you get this apparently very precise answer, but it's very hard to know if it's for the right target. So I very much like the idea of certainly exploiting large volumes of opportunistically collected data, but anchoring them in a much smaller randomized survey. And I think there's a little bit of an analogy, I wouldn't want to push it too hard, with case control studies, where if you've got 100 cases and 1 million controls, you might as well just have 400 or 500 controls, right? Because once the control case ratio gets above 4 or 5, the extra precision of having more controls buys you very little. And I think there are certain analogies there that clearly all data potentially convey information, But unless you're sure that it's unbiased information, precision is an illusion. And a long time ago now, Stefan Lauritsen, a distinguished Danish statistician, in a conference said to me, you know, one day, Peter, we're going to have a theory for efficiently throwing away data. And I think we're at that point. I really do. So I think there's a danger of assuming that high volume of data means high information content. Right? Now, speed, of course, is of the essence. And that's another reason that you might, even if you know you're losing some information by thinning your data, if it means you can make a decision tomorrow rather than next week, that might be a good trade-off. So I think there's a lot of work to be done in terms of balancing operational efficiency against theoretical efficiency to get a really smart real-time surveillance system for emerging infections.
Thank you. If there are more questions, I don't see anything on YouTube.
Paulo, I have a question, please.
Yes, please.
Okay, thank you. Thank you, Peter. It's nice to hear you again. It's a nice talk. I enjoy pretty much to hear you. And I have a question, a general question. Is there a place for classical geostatistics when you have so many methods like model-based geostatistics, preferential sampling? So what do you have to tell about it?
Well, I think what I feel about that is that purely statistically, I would argue no. I can see no reason I can't see why you shouldn't use established general statistical principles of modeling and inference to solve geostatistical problems. However, people who call themselves classical geostatisticians are typically not statisticians. They're typically earth scientists, mining engineers, and they have a huge insight, knowledge, and expertise that statisticians don't have. So I think that classical geostatistics is practiced by people who really understand the geo, but I still think that their statistics would be improved, perhaps not by much, but certainly would be better if they used what we call model-based geostatistics, which really is just a shorthand for geostatistics is statistics. And it's the problem and the scientific expertise that allows classical geostatisticians to solve hard problems. I don't see any inherent virtue in their inferential framework.
Thank you.
Thank you. If there is a last very brief question, we can go with it. Otherwise, yes.
It's Paulo Ribeiro here from Curitiba.
Go ahead.
Hey, Paulo. Apologies.
Thank you so much for being with us again, Peter. Great pleasure to listen to you. Peter, this COVID analysis is showing us something very challenging because usually we had models which could treat somehow some sort of interventions. So you would have breaking points in the process because you have an intervention. But apparently at the COVID age, the interventions are happening all the time and at different times within the same region. So it seems like there is a challenge concerning fitting the models with so many intervention actions. Would you have some comments on this?
Yeah, this is where you really do need something that's explicitly spatio-temporal and is able to handle time-varying covariates, because you're right, you're basically having, and so I don't know what's happening in Brazil, but in the UK now we have policies which are not countrywide, they're operating in local regions. So Lancashire, where I live, is now operating under different restrictions than Yorkshire, which is 50 miles away. And so you really have to have a very nimble system, going back to Renato's question, where you can actually, firstly, collect enough unbiased data that you can trust your prevalence estimates, and secondly, to understand their relationship with spatially and temporally varying covariates which codify interventions. And there are a lot of people in this country, and I'm sure in every country in the world that has a suitably qualified people working to try to crack these problems. And the interesting thing that we're at in the UK now, I think, is a bit of a sort of a debate point about whether you should be solving these problems with highly mechanistic differential equation models or with more empirical models of the kind that I use, because they're the only ones I understand. but they need to be more sophisticated than just straight out of the box. They do need to tackle the problem you've mentioned, the problem Renato's mentioned, and to synthesize multiple data sets in an intelligent way. But it's not clear to me that the deeply mechanistic modeling based on differential equations is actually adding much. And the thing that's publicized all the time in this country, and I hate, loathe, and detest, is this mythical R number for the country. There's no such thing. There's a surface R of X, which is different for every part of the country. And to summarize it by one number and make a countrywide decision is not, in my humble opinion, the best way to tackle the problem. So we need localized information, feeding local decisions and feedback loops all the time.
Peter, can I add one thing here? I mean, if you do have a very biased data collection, you can apply your preferential sampling to correct that.
Yes, but in theory, yes, but the preferential sampling parameters are very poorly identified unless you have a second data set, as I did in the environmental monitoring example, or a strong Bayesian prior. And this might be a situation where you can justify a strong Bayesian prior. I mean, for example, one of the data sources that we use in the UK is people self-reporting through a phone app. And over time, you can see which demographics are over-reporting and under-reporting, and which areas are over-reporting and under-reporting. So there you can probably start putting in a strong Bayesian prior for, the degree of non-representativeness of your sample, but it's you have to do one or the other. You can estimate a preferential sampling model from a single data set, but the likelihood is pretty flat.
Great, thanks.
Any last question? Last call for the last question. Okay, so I think we will close then. Peter, thank you very much once again on behalf of our BRAS and on behalf of all of us that had a very nice last hour listening to you. So really, thank you very much, and we hope to see you in person here as soon as possible.
And I hope so too. I apologize again for overrunning, but it's a real pleasure to reconnect with you and friends. Yeah.
Nothing to apologize, not at all. Thank you very much, Peter.
Bye.
Thank you. Então, passando agora para português, eu acho que nós vamos dar início à Assembleia Geral de forma imediata. Então, inicialmente eu gostaria de pedir desculpa a todos pelos 20 minutos de atraso. Eu optei por não interromper o Peter, porque acho que a apresentação